sure.
This line width and length scale, there's a relation. And is it a universal? I mean, is there a,
Well, it's measured in the Milky Way. I don't know. I'm not sure anyone can tell you whether it's universal or not.
okay? So this is
I would be surprised if it is, but I don't think anyone knows.
but the proportional constant is can be determined by the observation. Is that correct?
Well, but it depends for the Milky Way, right? So it's for the Milky Way abundance of dust, for the Milky Way metallicity, for the Milky Way radiation field. And how it depends on those parameters, I don't know.
So you only apply in the Milky Way.
Well, the one which is measured in the Milky Way, and then I think there's a few measurements in maybe Andromeda and some other nearby galaxies. But it's much larger. Those are actually at much larger scales. So you should ask Prof. He knows much more about that.
Okay, I don't know much about halos, it's not my field of research, but am I correct in thinking that the basic idea is these halos form first and the galaxies form from the halos? Or is this...
Well, they form together, right? So I don't think it's correct to say that halos form first.
And the halos are generally much bigger than
the dark matter halos, yes.
Much bigger than the galaxy?
Yes, factor of 10 bigger.
The centers don't coincide? So
No, centers coincide. Of course coincide, yeah. Okay. It's at the depth of the potential well, right? It's only one gravity affects both. They have to coincide with very high precision. Okay, well let's keep going, right? The sooner we are done, the sooner we get dinner. Hello? Let's keep going, right? So I already cut a few slides out, but I cannot cut out everything, right? So we have other tough topics ahead of us. So that's basically the main physics that you need to take out of that. But if you actually do it in the simulations, there's some numerics you have to be aware. Right? So what I actually didn't talk about is how to define the Coulomb density. And, in particular, how to define it without doing ray tracing. Of course, the best way to do it is to actually run a ray tracing in your simulation that your simulations evolve. Just that it's not very practical because you won't be able to do anything better than 10 cube or something like that. So what we used, and the suggestion I'm making, is to use something I call Sobolev-like. It's not actually a Sobolev approximation in its original sense. So you define the Coulomb density as a density times some scale, and you want to choose a scale wisely. So a good choice is actually to take something like the inverse scale length of the density. Right, so define it as rho over gradient rho absolute value, and you put coefficient here, which you actually have to calibrate from actual ray tracing simulation. But in this case, you only have to do ray tracing just to get one number. And so when we do that, that's what you find 0.5. Let's give you an example of how it might look like. This is a true Coulomb density through ray tracing, through cosmological simulation. This is the Sobolev length, right? Each point is just one line of sight. And so you get this general trend. You can compute the average and RMS. The dashed line, which you can barely see, is a 1-to-1, is this 0.5 factor. Right? So it's not a very good approximation, but it's okay. Right? So you can live with this one. Because otherwise it would be way too expensive. So just a bit of caution. So what you gain from using this, you actually gain very weak resolution dependence. So here are simulations which have resolutions from 30 parsecs to 500. Right? And this is 3 different dust abundances, radiation fields. And they all show the fraction of H2 as a function of density. So if you see, if I start going to really high resolutions like 500 parsec or 260 parsecs, then I get big deviations. But anywhere up to 130 parsecs actually coincide reasonably well for different parameters. And so what occasionally people use is this. Right? They take your simulation, take a density in your cell or SPH particle and multiply it by cell size with a smoothing length. So this is a very bad idea. Okay? So there are actually papers that use this. Because here you introduce explicitly dependence on your resolution. Now imagine you are running your resolution for your thesis, right? You're doing really hard, you use something like this, and then a friend of yours walks into your office, right? Tells you, you know, I have a problem with my code. I had some bug I cannot find, and I have this zillions of CPU hours on the next nearby supercomputer center. Can you actually use them? Because otherwise I will just take them away if I don't burn them within this month. Say, oh, of course I can take them, right? Who would refuse free supercomputer time? So you go and say, well, it's a lot of time. I have to burn it really quickly. So what I'm going to do is I can now increase the resolution of my simulation and get something which is twice better. So you run your simulation with half the resolution, and suddenly all your molecular clouds disappear because you decrease the comb density by a factor of 2. Right? And now all your hard work just goes to nothing because you now don't have any molecular gas. So this just tells you it's a very bad idea to tie your physical models to a resolution of your simulations. You should try to avoid it as much as you can by using tricks like this. Right? Again, it's not perfectly resolution independent, but it's much more resolution independent than doing this in an explicit way. So just be aware of that. And that's not necessarily, doesn't only apply to this atomic to molecular. It will apply any time you need to say estimate the column density. Please don't do that. Right? So then in terms of what you want to use, right, if you want to run a simulation, well, one thing you can do is to actually put all this physics, all the equations into your code and wait for a long time, but you don't have to do that. Right? So there are now two separate parameterization of this transition. The first one was introduced by Mike Kramholz and co-validators in 2009. It's actually an analytical model, right? So you can just write a closed formula. And this model comes in two different flavors, which are often mixed up, right? So you have to be careful. There's actually a full model that accounts for this transition as a function of both radiation field and dust abundance. That's what I call light model. That actually assumes that radiation field is a function of density and metallicity. And the way to distinguish this, if you open someone's paper and you see this formula, that's a light model. Right? Then again, there is our work, in which case we actually ran full three-dimensional cosmological simulations, about 40 of them, in fact, right? To calibrate H2 abundance as a function of radiation field and dust abundance. And then a couple of years ago, Mark and I actually compared these two descriptions. And to my great disappointment, they found to be almost identical. So the Mark just did it on 2 sheets of paper, and I spent hours, no, not hours, thousands of CPU, probably hundreds of thousands of CPU hours, running the simulations and doing analysis, and in the end it was actually the same. But on the other hand, that's actually good. It just tells you that we more or less understand what happens. There's also this light model, which is even funnier. Right? So the Mark has this idea how radiation fields should depend on density and metallicity, which I don't understand at all where it comes from, because I know if you look at high-redshift galaxies, radiation fields varies by orders of magnitude, by at least 1 order of magnitude. Nevertheless, whenever we try this formula in the simulations, it worked pretty well. So there is some kind of magic there. Either Mark got a revelation, he now knows how radiation field changes, or there is some kind of magic here that this model actually works too. Right? But it probably wouldn't work in all environments. It wouldn't work like in stubborns and big mergers. But it does work in normal ISM, right, for whatever reason. Again, it's something I don't understand. So if that, if I was giving this lecture on 25th of February, that actually would be the end of the story. Right? But on 26th of February, 2 weeks ago, something happened. Right? And so for now, look again at the plot I showed you before. This is a feed of Drey-Bertoldi to the self-shielding function. Again, this is power law approximation to it. This is dust absorption, right, exponential. It's this part that kind of bothered me for a little while. And then I talked to Bruce Drain, and then it became clear. Right? It's this difference at very, very high column densities that is kind of bothersome. So let's see if you can figure out what's going on there. So the answers are angular momentum is conserved, and our usual answer. Line absorption becomes continuum absorption. Right, lines. Again, I remind you, right, the reason why this one is so steep, because it's continuum absorption, dust absorbs all photons of all energies. And the reason why this one is so gradual, because it's a line absorption. So individual lines can become optically thick, but there will be some other lines nearby which will become optically thin. So what's going on here? The second question, line absorption becomes continuum absorption. Line saturate, H2 dissociates, and then this just feed becomes inaccurate. Okay, who's for A? 1. The good thing you know is that the right answer, right? It's just the right answer to a wrong question. Okay, B. No one's for B. C. 1. D. 1, 2, 3, 4, 5, 6, 7, 8. E. 1, 2, 3, 4. Yeah, you're not brave enough, right? So it's like you're voting for your life or something. Well, okay, this is actually a sign wrong, right? If H2 dissociates, it will be less absorption than less shooting than more. So in this case, it's a case of anti-democracy completely because the right answer is B. And now I'll explain what actually happened. There's some interesting physics happened there. So if the Coulomb density of molecular hydrogen is really high, right? So it's again the same plot. Remember why self-shooting was inefficient, right? It's because these lines didn't block light photons which can destroy these lines. It will be absorbed by this transition. Like the line is a transition, atomic transition. Right? So each of these black bars corresponds to the level, which if excited can lead to the destruction of the molecule. So this patch of the region, of the H2 region, did not block this one. That's the main thing about line absorption. So what actually happens at very high Coulomb densities, that line acquire they acquire the wings, damping wings, right? They start feeding the width of the level. The same happens in damped Lyman-Alpha systems, right? This W quantity in the line profile, which when we talked about, if you remember, when we talked about GM. So when the Coulomb density is really high, the lines become really, really wide, right? It happens only at very high Coulomb densities. So if the lines become really wide, they start overlapping. And when they start overlapping, they're essentially behaving as continuum absorption, almost continuum absorption. You get most of absorption at low wavelengths, maybe a few holes here and there. And so now this patch of the molecular cloud actually can block a substantial fraction of photons which would destroy these molecules in this patch. And if you imagine going further, somehow PowerPoint didn't let me make those lines even wider. Then eventually they will all overlap, and then it will be like a continuum. So H2, this line absorption becomes essentially continuum absorption. That's what explains this drop in Bertholdi and Rein feed. The feed is actually accurate to much higher Coulomb densities. So that's called the line overlap. And so after a conversation with Bruce, the proper way of treating this function is actually this way. So this x parameter should now be treated in two different ways. There is one x which describes the line absorption, line shooting in the non-overlap case. It's x1. That one depends on the sonic length. And this exponential part should depend on the total Coulomb density because now whole of the molecular cloud shields itself. Right? So now all of the molecules help shield all other ones. And when you do this and put it in the simulations, you actually get a very different result. So the effect of this line overlap is that this dependence on dust disappears for dust abundances about somewhere around 20% of the Milky Way. So basically the small Magellanic Cloud is the lowest metallicity galaxy in which dust absorption is still important for molecular hydrogen. And if you go to even smaller metallicity galaxies, dust becomes irrelevant. It's still important for formation, right? Molecular hydrogen still forms through dust channel, but the dust shielding actually does not dominate. Self-shielding completely takes over. Which means that as of this February 26, neither of those fitting formulas are actually correct. So there's a simple fix. If you ever need to do it tomorrow, it's a simple fix. What you have to do is to basically max the point or not allow it to go below 0.4. So if dust abundance goes below 0.2, that means that self-shooting is equivalent to dust absorption. It's about 20% of Milky Way dust. And then there will be better things coming soon. But there's a great utility for this project, especially for those who are in first, second year, because that's all you have to be checked over the night. The inventory formula is already different from this. And that's this idea of the overlap, so it's possible, but it needs to be checked. And this it's very easy or relatively easy to check. If you just take one of those turbulent GMC simulations that Ralph showed, you can post-process them like this idea of transferring these H2 lines. Doing it self-consistently is impossible. It's way too hard. But doing it in post-processing is possible, right? So you just shine radiation on one side of this simulation box, and you let all those lines absorb, including all those redshifts of these lines due to motions, supersonic turbulent motions. And then you'll be actually testing this whole theory of H1 to H2 transition. You can also do it in different radiation fields and different intensities, but just rescaling, say, the amount of metals in your simulation. And so if you do it this way, then you can test all this line overlap and basically recompute all these fitting formulas essentially exactly, right? And first of all, we may make a terrific PhD project, a very cool one because it's very rich in physics. But then when you come up with fitting formulas from that project, everyone will use them because it will be by far better than anything else. And so you'll get hundreds of citations for free. Okay, almost, right? Well, some amount of work you have to do. But it's actually a very interesting physical project. Okay, so this is the end of this H1 to H2 transition. And a couple of topics I'm going to go briefly, and then we'll talk about this Pandora box of cosmology. So what do we get from that, right? So we spend so much time modeling molecular hydrogen in your cosmological simulations. What do we get? So we actually get quite a few things. So first of all, this is a cartoon of multi-phase ISM. Ralph talked about this more quantitatively, just taken from an undergraduate textbook. You have density, you have temperature, you have different phases as hot coronal gas, normal warm neutron medium, right? This cold neutron medium molecular gas, etc., H2 regions. So now we can take the simulation that fully accounts for this molecular hydrogen formation, and you get those phases. Not only you get things in this region, you actually get phases, right? So if you look at points, right, there are breaks between them. So there's really a cloud of points here, a cloud of points here, and a cloud of points here. So you're not only getting the right distribution of temperatures and density, you actually get them as phases automatically. You even get this stuff, which is called dark clouds. I don't know what actually they are. So, but in the simulation, it's actually a numerical artifact. It's where the subcycling solver breaks down. Right? So it's not real. So this is a good kind of good news because you get all those phases if you model this molecular hydrogen formation. There's also lucky coincidence. Ralph already mentioned that. Right? The fact that so why do we actually care about this at all? Right? There is this lucky coincidence that it's the same shielding by dust and self-shielding. The shielding works in two ways. First of all, it's needed for H2 formation, but also needed to suppress photoheating, photoelectric heating. So it's needed for two things. And with one shielding, you kill two birds. Right? So you make gas molecular and you make gas cold. And of course, to make stars, you have to make gas cold. And so this coincidence implies that that the gas from which stars form is very likely to be molecular. So the molecular gas is not actually needed, right? Ralph already mentioned that. It's not needed for forming stars, right? Just a very good tracer. You can think about molecular hydrogen like a paint someone splashed, right, into the cosmic gas. And whenever the paint went, that's where stars formed, right? Not because the paint was there, because it was splashed in a smart way. Or sort of a coincidence way. Right? So it's maybe just a coincidence in some sense. But it's not just a coincidence because it's all based on the same physics, right? It's shielding that we need both to keep it cold and to keep it molecular, and to make it molecular. That's why this molecular gas correlates very well with star formation. Right? So there are a few corollaries you can take. So first of all, molecular clouds have to be turbulent because of that, and they must be supersonic, right? Because they cool rapidly, so you get to cold phase, whereas you don't change the velocities right away, at least immediately. So at least in the beginning, they have to be supersonically turbulent. And then turbulence which means that turbulence is short-lived if it's supersonic, so it either have to be driven or molecular clouds are short-lived. So turbulence in normal ISM and warm neutral medium then has to be subsonic or near-sonic, and hence long-lived. And the corollary number 3, to which Ralph might not agree, there cannot actually be large amounts of this cold neutral medium. Also, there are some observations that claim that. Right? And so what really is this stuff is actually, I think, an open question. Okay, so let's see how I'm going. I have a piece to skip. I'll go really fast about one really funny thing, okay? It's a thermodynamics of H2. Right? So we know H2 is a diatomic molecule. And in this case, the thermodynamics can be solved exactly. Right? So if you now take ideal gas, and you all presumably studied ideal gas. Right? So there are 4 statements about ideal gas, one of which is wrong. Let's see how well you know your some kind of physics. If you actually go to Wikipedia, you'll find all 4, but one of them is wrong. You need to make a choice? Who is for A? So the question is, which one is wrong? Who is for A? Okay, I will read them. So the A states adiabatic index gamma, right? It's Cp over Cv. The Cp and Cv, you know, it's heat capacity, specific heat capacity at constant pressure, at constant velocity, right? So the standard notation. Cp is equal to Cv plus 1. For monatomic gas, Cv is 3/2, and for diatomic gases, Cv is 5/2. Okay, who's for A? 1. Who's for B? 1, 2, 3. Wow. I would say 25. Who is for C? Who is for D? 1, 2, 3, 4, 5, 7. There are more people in the room. Huh? Okay, we'll see what the answer is. So how do you actually compute those things? Right? Well, we compute those through a quantity called partition function. Right? And now we actually have to deal with quantum mechanics of gas. So the partition function for diatomic molecule is e to the minus n t for given level n. It's a electronic level. So we assume that both H atoms sit in n equal 1 state. Then there is a contribution because there are rotational levels which can be excited, and there are contribution because there are vibrational levels which can be excited. So the vibrational part is actually very easy. It's just sum of all vibrational levels. It's h omega v is the vibrational quantum number over temperature, and I use energy units for temperature to forget about kb. So the rotational part is actually quite tricky because H2 is symmetric molecular, and in quantum mechanics you know that 2 protons are actually indistinguishable, right? So if you have H2 molecular and you flip it like this, you cannot distinguish these states from that one, right? They're completely indistinguishable. And that makes it a little bit tricky because it turns out that depending on what the the spin of the sum of the spins of the 2 protons is, if they aligned, so get 1/2, 1/2, 1 total spin of 2 protons, then you can only have odd rotational numbers, quantum numbers. And if the spin is 0, if the 2 protons have anti-aligned spins, then you can only populate even rotational numbers. So that essentially makes out of 1 hydrogen molecule 2 subspecies. They're called ortho hydrogen and para-hydrogen molecule. And they, in many respects, behave as completely different gases, right? So it's very hard to take one and to get into another. It's a very strongly suppressed transition. So then the rotational sum for the mixed, but they are usually mixed. In reality, molecular hydrogen has a mixture of both. And it's usually 3 parts of ortho to 1 part of para because of the way quantum mechanics works. So you can write this partition function for ortho is just the sum over quantum numbers, again, over temperature. This is moment of inertia. But this one is over odd, this one over even. Again, this is relatively straightforward to do. Right? And then you get the partition function. So what do you use it for? What is it good for, actually? You know, why did I even talk about it? Right? So let's see. This is, I'm not sure it's the last one. So we'll have to do it fast, right? Because, so who is for A? One for A. Who is for B? C. There was a one for A, right? Who is for C? 1, 2, 3, 4, 5, 6, 7, 8, 10. Who's for D? Oh, many. When you become professors, right, and you give quizzes, if you really want to piss off your undergrads, that's the way to do it, right? So you give 3 answers which really baloney, and you give one which sounds correct, right? And this sounds serious, and everyone, of course, will pick up the one which sounds serious, right? But this is wrong, right? The right answer is actually C. So the partition function is a function through which all thermodynamical properties of the gas are derived, right? You actually derive everything. All we need to know is the Z function to know everything about this gas you ever want to know. So you derive free energy, from which you derive pressure, entropy, you derive total internal energy, you derive the specific heats, TSP, everything. And so if you notice that this free energy actually depends on the log of Z, and Z is a product of contributions from different rotational times vibrational times this motion in space, etc. So the specific heat is actually becomes the sum. There's a 3/2 contribution, just like in monatomic gas, because it's a translational degree of freedom. There's contribution because of rotation, contribution because of vibration, and those you can compute because you have those series. All you have to do is to take this series and compute them at a given temperature, and when you do that, you find that H2 is never behaves as a diatomic gas. So in the first quiz, the wrong answer was D, right? So C sub V is not a 5/2 for any diatomic gas. For H2, it never behaves like a diatomic gas. So this is C sub V as a function of temperature, and this is E over T, which in actually ideal gas with constant sub V, those would be equal. And here they are not, right? Because the quantum mechanics for H2 is such. So H2 is actually very weird. So at temperatures above 20 Kelvin, it doesn't even have any region where it behaves like 5/2, right? 5/2 would be whatever here. Right? And at lower temperatures, it behaves as a monatomic gas because even the first rotational level is not excited. So if you don't excite the rotational vibrational levels, you just kick the molecule together, then of course it behaves like one atom. You don't care whether it's how many pieces it has. So the interesting thing about H2 that it either behaves as a monatomic gas or it's really very complicated. So we now go to the last part of my piece on the ISM. So my next lecture will be on affirmation. And that's called cosmic Pandora box, and it's X factor. I'm going to go a little bit fast because I think we are running out of time. So there's this classic catch-22, right? So H2 has to be shielded to exist, right? From the radiation from outside. But at the same time, it means that it's outside, which includes us, right? Then cannot see emission from this molecular gas, because if H2 is shielded from us, then we are shielded from it, right? It goes both ways, right? Just this common density between us. So we actually cannot see Lyman-Venn emission from molecular hydrogen, because molecular hydrogen exists. So on top of that, right, let's say, okay, I don't see the emission, I just find a quasar behind it and look at absorption. You can, in principle, do that. There are a few lines of sight that it's possible to do that. But for most quasars, you have so much dust that in this cloud that actually it also blocks the quasar itself, right? So actually wouldn't see, you won't find the quasar behind this black spot in the sky. So and it's also very hard to do absorption spectroscopy to measure amount of H2. And so the standard way to observe molecular clouds is via the CO emission. Again, Ralph talked about this today, so I'm just repeating this very briefly. Right? This is rotational levels of CO. Right? And the first transition from 1 to 0 rotational level happens at 115 gigahertz. It's 2.6 centimeters. It's almost exactly 1 inch. Right? So Americans know what to choose as a unit length. And then, of course, they have all other transitions, which are just proportional. What?
Can't be centimeter. I mean, the zero transition is in millimeter band.
Oh, shit, I'm off by another minute. Right. It's millimeters, sorry. Okay. right. It's 1.4 gigahertz is 21 centimeter. So, okay, so CO, of course, exists, but there's no reason why it should be a good tracer of molecular hydrogen. Well, first of all, CO also needs dust shielding to exist, but actually needs much more dust shielding. So you can have molecular gas which were distributed enough to exist as molecular gas, but CO will still be dissociated right there. And then CO also gets saturated right, at very high Coulomb density. So if you have a lot of molecular gas, you can only get a fraction of it emitting in CO. And so CO emission comes from a very relatively narrow range of Coulomb densities. Right? So normally we would expect there would be no correlation whatsoever. Right? Again, this I think Prof showed something like this today. Right? This just shows you that if you take molecular clouds and increase the size, so at first you get a cloud, and this one is molecular hydrogen, this light blue. It contains molecular hydrogen but no CO at all. Then you start getting things like carbon plus exists here, you get neutral carbon, and then CO is dark gray, so in the small clouds you actually don't have any CO at all. And then in the big ones you get a lot. And the same happens if you actually increase metallicity or dust abundance. Right? So this actually delta DGI is what I call DMW. However, miracles do happen. Right? So we know empirically that it is a good tracer. Right? So this gives us an example which shows the CO luminosity versus the video mass of galaxies that are gas dominated. And you can see that there is a very strong correlation between the luminosity in CO and total mass of the gas right, at the centers of those galaxies. And they go all the way from nearby spirals, there's LMC, etc. Right? There's a bunch of galaxies which change vary in mass by many orders of magnitude. So it seems to work really well, right, surprisingly well. Right? And so one of the reasons probably is because in each individual molecular cloud, there may be a wide variation between how much CO emits and how much molecular hydrogen you have. But when you average over the whole galaxy, you reduce this difference. So that may be part of the story. So the quantity that's often used in galactic studies is this XCO factor. It measures the Coulomb density of H2 towards the equivalent width of line of CO. So you take your telescope, you look at the molecular cloud, right, and you measure the H2 Coulomb density somehow, if you can do that. And then you just measure the amount of CO emission that comes, you divide this, and you get this conversion factor. So then if you know this number, you can take another cloud for which you don't know the Coulomb density of molecular hydrogen, but you can still measure the amount of CO. You take the amount of CO, you multiply by this, and you get magically the Coulomb density of molecular gas. And this is just, again, the equivalent width is just integral of the antenna temperature over the width of the line in velocity units. Antenna temperature just measures the amount of radiation in radio that you get. So just a unit radio astronomers use to make sure that radio astronomy looks very different from optical astronomy, right? So, so that everyone gets confused. So that's galactic value. The value that is used in the galaxy is 2 times 10⁻20 in those weird units, right? So it's even worse than the Hubble constant. So it's centimeters here, kilometers here, so tons of constellations you can make. And then in extragalactic studies, right, you usually don't resolve individual molecular clouds in the galaxy, at least without ALMA you cannot do it. And so very often you just take all the CO emission from the whole galaxy, and you want to convert it into total gas mass. So this is a conversion factor. It's 1.36 comes from the fact that this is molecular hydrogen, but you also have helium. So if you add helium, then you actually get, which is assumed to be mixed with molecular hydrogen, then you get this 1.36 factor in addition. And so again, if you know this number, all you have to do is to measure the luminosity from this galaxy in this radio line, and you multiply it by this factor, and you get the mass of the gas. Right? And again, this galactic value, so this number, in fact, is just exactly proportional to this one. Right? So there is just unit conversion between them. So that number corresponds to 4.3 in those units. This is so masses per parsec squared, kilometers per second. So if we now want to model this, now what we want to do is to actually say, okay, observe the CO emission. We have simulations in which we have molecular hydrogen, sorry. But now if we want to compare apples to apples, we need to know how much CO our simulations produce, our estimated galaxies. So the scales in which CO emission originates, it cannot be resolved in cosmological simulations, in galaxy formation simulations right now, they are very small. But CO emission is not important dynamically. So what we can do is to model this in post-processing. We run the simulation with all the dynamics that molecular hydrogen provides us, and then in post-processing, we can paint CO on the simulation outputs. And for that, we need a subgrid model, because we can resolve those scales. And in principle, the best subject model for anything is someone else's simulation. So if you want to have a subject model for star formation, the best thing you can do is to go to star formation guys and say, well, what's your best simulation? I will use it in my subject model. It hasn't happened yet, but it's actually going to happen soon. Right? So we're at this point where we can use their simulations to use as our subject models. So the simulation that we used, I want to talk about is this Glow and McLaw. It's actually a whole series of simulations, a series of papers. So it's a 20 parsec box of the piece of the ISM, which includes a lot of physics, including radiative transfer and some rather crude approximation, but a lot of reactions for this formation CO and other molecules, and they all interact dynamically. So it's a lot of subcycling, a lot of chemistry in it. And then what they can do is then they scan the parameter space. They use different metallicities, different densities, different radiation fields, and basically they can take for value for the mean density on this scale, and for given metallicity, how much H2 I have, how much CO I have, and I can make this average XCO factor on this scale, which is comparable actually to scales of resolution of cosmological simulations. Actually a good match, because their box size is now one resolution element. So that's just a beautiful picture. So this is the equivalent width of CO. This is Coulomb density. That's actually X factor, right? This is Coulomb density in CO. This is Coulomb density in H2. So you divide this two, you get this thing. And then what they found, the main result of their paper, is that this XCO factor, averaged over this 20 parsec scale, is primarily dependent on the AV. That's it's absorption by dust of the visible light, which is actually very close to the optical depth of dust in the Lambda band. And what they found, and this is the main thing, so what matters mostly is the amount of dust you have, which kind of makes sense because I said it's important for H2, it's even more important for CO. Right? And then it's done for different densities and different metallicities. As you see, there's a relatively wide range of parameters sampled. So what we can do now is to take those simulations and put them in a subgrid model, which we've done, Robert Feldman and the Kravtsov, and that's how. And then we can predict this how XCO factor changes as a function of metallicity, as a function of other parameters, for example. And this green bands is what this model, right? It's kind of our model, but it's all based on Glover and McLaw simulation. So if something wrong with it, you should blame Glover and McLaw. It kind of agrees with kind of measurements, but there are a few measurements here and there which are not very conclusive yet. With Zalm, it will be much better. So using this model, you can kind of understand what happens, right? Maybe. So there is indeed this power of averaging. So this X factor depends on Coulomb density of H2, it depends on metallicity, depends on radiation field. So you see it varies enormously by, this is actually log, by several orders of magnitude, the function of Coulomb density, different metallicities, different radiation fields. But when you average it, and that's what happens on sort of 50 parsec scale. But if you average over kiloparsec scale, most of this variation disappear. Right? Just have the power of averaging does give you just one, not just one value, it still depends on things like metallicity most sensitively. But it does remove most of variation, say with Coulomb density and with radiation field, for example. So there is a lot of that, which is probably contributes to this magic of why XCO works. I must say that in this story, the situation is different. There is also an alternative model, just like an H2 formation. But these two models don't agree at all. They have signs different. So this is our model that actually predicts that X factor grows this, after this first transition, it grows up with Coulomb density. There's oh, I didn't put a reference, right? It's Narayan, Kramhertz, might be Penk-O and Fernquist. So in this alternative model, it actually goes down. So we make different predictions about even the rate at which it changes. H2 models, both of them agree, but it's XCO models, they disagree as much as they can. So depending on which one you choose, you can get anything you want, first of all. But then the truth is probably somewhere in the middle. So if you actually compare them, right? So our model is based on small-scale simulations. They're just analytical model. Our model does account for radiation field, and theirs doesn't. But they do account for coupling between dust and gas, and we don't. simply because this Grave and McLeod simulation didn't account for this coupling, so we could not do anything. We could not go on those simulations and do that. So they probably should be considered as right now as upper and lower limit. Right? So they're both extreme. And there's probably somewhere in between. I don't know how I would plot. We do agree with some kind of measurements, but this trend, Ryan's trend, is actually better for Euler's in my next story, which I try to squeeze in the last few minutes. And so the truth must be somewhere doing something like this one. Maybe, right? But basically, this is something that needs to be resolved. It's a controversy right now in how CO factor should be, CO emission should be modeled in cosmological simulations. So there are two small pieces I want to go over. So I call this Pandora's squared box. Right? So it's even worse than the X factor. It's the X factor in Euler's, which stands for ultraluminous infrared galaxies. And I call this ODP, which stands other dense places. So the X factor depends on the cone density of H2 and the equivalent width, which is basically amount of radiation times the width of the line, delta V. So most molecular clouds in the Milky Way and other normal galaxies are very cold. They have temperatures, gas temperatures of 10 Kelvin. Right? But cosmic dust is actually warmer. I think Ralph also mentioned today. Dust has temperatures 40, 60 Kelvin. So if they couple at high enough densities, then you can actually heat the gas by coupling it to the dust. And so if this happens, then this brightness temperature can increase and XCO factor will actually go down. So this whole story about this ultraluminous galaxies and dust gas coupling was actually started by Solomon and Dons and collaborators in '97. They opened that Pandora's squared box. By looking at ARP 2200, ARP, what is this galaxy? Whatever, 220. One of the nearby mergers, right, with ultraluminous infrared galaxies. And so what they try to detect CO and they try to measure the amount of molecular gas by measuring studying the dynamics of this galaxy. So you can actually compute both the mass through dynamics and then the actual emission by measuring how much emission you get. Unfortunately, you still cannot, at this time, they could not do it properly because it's still dependent, they could not resolve the galaxy, so dependent on kind of factors they had to put. And each of those factors kind of factor for 2. Right? So we have a factor of 2 here, factor of 2 there, and you very easily get something to factor for several, right, together. And this paper is surprisingly often misinterpreted. So they basically took this minimum value and forgot about these factors. In part because it's a very nice paper. They went through a lot of math to do things right. But then it's not actually very well written as a text, right? So in the conclusions, especially in the abstract, it's a little bit misleading. So if you only read abstract and conclusions and don't go through the paper with a pencil, then you actually get a wrong conclusion from the paper. So for a long time, there was this idea that, based on this paper, that this alpha factor should be lower in this ultraluminous infrared galaxies. But because of this controversy, because of the problems with these measurements, it wasn't actually clear whether it was true or not. And finally, this was resolved last year, right? Thanks to Herschel, to this one, to that one. Right? Because with Herschel telescope, you can actually now directly detect the emission from the dust. Right? So this is one of the spectrum of one of the galaxies, which was named after me for whatever reason. It shows the emission of this peak is emission of dust. So you can actually, by modeling the spectrum, you can actually measure how much dust you have directly. So what you do from this type of observations is you measure 3 things. You measure metallicity of the galaxy, you measure the amount of dust. Of course, you can measure the amount of CO by pointing radio telescope. So unfortunately, it's still 3 quantities. Right? So it's not yet enough to do everything. So you have to make assumptions. So let's say you assume that you know how much dust per gas you have. So you say it's the same ratio, say, as the Milky Way scaled with metallicity. Then if you know this, then you know by multiplying it by dust, you get gas, and taking those two together, you get this alpha CO. Or you can take the other way. You can assume you know what alpha CO is, then you can actually get dust to gas ratio in the galaxy. But you cannot do everything. And so what they find is those measurements. This is a case where they assume alpha CO, and they get gas to dust ratio. right? Or they can assume dust to gas ratio, and then they actually get alpha CO measurements. And then if you combine everything together, if you say, I would use this way, I assume I know how much dust per gas I have. Sorry if I go too fast, but I think we're running out of time. Then you get this a few measurements here and there. Okay? And you do see that there are actually changes. So this very luminous galaxy, this is star formation rate. That's actually a specific star formation rate. Star formation rate divided by stellar mass. But for now, forget about it. Think about the star formation rate. Those are really bright star-forming galaxies, and those are just normal ones. So again, the Milky Way value is somewhere around here, where most of those points are. So those points are the normal galaxies. You have normal XCO, alpha CO. Right? XCO and alpha CO are the same thing as synonyms. And then you have these low values, which is significantly lower. Right? It's the first real measurement of this low alpha CO in other galaxies, right? In this ultraluminous infrared galaxies. So this one is actually now real. And so then you can, having these points, you can do two things, right? You can say, well, this is just a trend like this, or maybe it's a constant value and then it drops down at some particular value. And you can make plausible arguments for both scenarios, but until you have more data, you don't know. Right? So what we know today is that this XCO factor, or alpha CO, is indeed lower in these big mergers, which are ultraluminous infrared galaxies. But what the trend is and how it changes these galaxy properties, we don't know. Right, and finally, it's my last slide. This is a cube Pandora box. Right? In addition, those galaxies, those infrared galaxies and submillimeter galaxies, not only they may have different alpha CO factors, but they also emit most of their energy not in the band which we observe in the Milky Way. So that's a distribution of CO emissivity over this rotational quantum numbers. And most of studies dealt with this 1 to 0 transition at this point. But these galaxies actually emit most of their radiation in like 5 to 6 transition, or 7 to 6, 6 to 5. So not only this radiation, this luminosity in this transition may depend in a wide way on the H2 abundance. But in fact, how much radiation emitted here may also change, because most of the radiation here is emitted in a different band. So we actually need to know how to transform this line luminosity into this line luminosity to even start talking about this XCO factor. So that makes things even more complicated, because now we have another conversion factor from some other transition to 1 to 0, which we use to define the XCO factor. So on this optimistic note, I'm finished. So basically we know nothing, which is really good for you guys, because you can actually do something to contribute to this. But the reason why it's actually important, not because someone really cares about CO, but because ALMA. So ALMA will measure tons of those galaxies at redshifts 2 and 3, 1, 2, and 3, where peak of star formation is. So ALMA will be an important, very important instrument in understanding star formation in gas and high redshift galaxies, and the time where most of stars are actually born. And of course, ALMA will see the CO, so we need to know what to do with it to understand what ALMA actually sees. So it's not only important as a theoretical exercise, it's very important for understanding, for analyzing ALMA data, figuring out what ALMA actually going to tell us. Okay, so that's it. We now have to I hope there are no questions, because I'm completely exhausted. Yeah, there are?
Could you maybe put a few more words on the gas to dust mass ratio? That for example, when we simulate a galaxy, do you find it okay to assume a constant factor, or would you recommend?
Well, I think what everyone assumed so far, was you know that abundance of dust should depend on the metallicity. If you have no metals, you shouldn't have any dust. So the standard assumption that everyone actually used is that the dust to gas ratio is just linearly proportional to metallicity in solar units. Right? If I do this, if I want to do it mathematically exactly, I would use this my quantity d Milky Way. This is a standard assumption. Right? So in the Milky Way, you have Milky Way dust. If you have galaxy which has 10% of the metals, you will have 10% of the dust. And if you look at observations, there are people who measure the dust to gas ratios. And for galaxies which are more metal-rich than 10% solar, it's actually okay. This relationship is good. But for dwarfs, which are less metal-rich than 0.1, then the scatter becomes very, very large, and it's not clear what the data tell us. So depending on the galaxy you're interested in, it may or may not be a good assumption. But that's the one everyone is making. So if you want to go beyond that, what you have to do is to actually model dust as a dynamical field in your simulation. You have to model creation and destruction of dust, just like you're following, say, atomic hydrogen or molecular hydrogen. You put dust as another dynamical variable. And that can be done. It's not very difficult numerically to do that. But so far, no one done that. No one tried that.
Following up on that,
Huh?
how do you form dust, or how would you put that into a system?
Well, so you have to understand something about dust. So what I think we know about dust, and Ralph might correct me, I don't know much, is that you first need to form a seed. And seeds of dust form in atmospheres of AGB stars. When the planetary nebulae go out, that's how dust seeds form. Plus, they also form in supernova remnants. But then after those seeds get into the ISM, most of dust forms by those seeds growing. They just accrete metals from that and grow in size by a factor of 100 or so. So what you have to do is to model the injection of dust seeds from supernovae, which you usually have in the simulations, and AGB stars, which you can also add, because if you know stars, you know how much, if you know, assume IMF, you know how much AGB stars you get. And then you also add some equation which allows this dust to grow. But also all relatively simple equations, right? So basically get some density of dust just growing with some time scale for dust formation, which depends on metallicity and temperature. So if you take Bruce Drain book, I think it's all there. And then there should be destruction terms in the hot gas and by radiation, etc. And so you can write a sensible equation, and there will be some parameters there which you don't know, so again you have to play and see whether you can say, if you model the Milky Way, whether you get the right amount of dust, and you can tune your parameters to make Milky Way right, and you tune your parameters to make SMC and LMC right, and then you probably have a reasonable model. We've actually done that, so the answer is completely relevant. So if we have this, it's all we need. Maybe someone will find a regime where it's actually important. Okay, we're done. We're ready for dinner.